Power system protection lectures. I'm Pratap Mysore. Today we will cover feeder protection. I should also call this as distribution system protection. If you look at the configuration of a distribution line, it is a 4-wire multi-grounded neutral system, or a 4-wire uni-grounded neutral system, or an ungrounded system. In the 4-wire multi-grounded system, there are 3 phase wires and 1 neutral wire which comes out of the substation, and then from which is connected to the grounded source, and then it is grounded at every pole outside the substation. In the uni-grounded systems, it is not grounded at every pole, but everything returns returns to the substation ground, neutral of the transformer, or of the neutral of the ground the source. And in the ungrounded systems, it could be a wire delta connected winding from the source. The distribution voltages are typically from 4 kV up to 34.5 kV, and these were traditionally radial systems. That means there was a source and we were feeding the load, and if a fault occurred, the fault current was always coming from the source, and then we used overcurrent relays or devices which detect an overcurrent, and that operated accordingly. This is changing very fast with distributed resources, with a lot of sources, non-conventional sources coming back on the feeders. So the system is changing. It is becoming bidirectional, and also with intelligent controls, we have we can tie 2 feeders also, making it as a bidirectional one. So the setting philosophies are also getting adjusted accordingly, but the basic philosophies remain the same. That is what I'll cover in this. The construction of a distribution network line is you have 3 phase conductors, 1 on the pole, and then there are 2 on the cross arm. This is a typical 8-foot cross arm that is used, and the 4-wire system has a neutral which is below this, and then it is grounded at every pole if it is a multi-grounded network. Here is an example of 336 aluminum with 2 ACSR in the neutral. Generally, the conductor current carrying capacity of the neutral is less than the phase conductor, typically half of it. As the phases loads are balanced, there will be no return current. Return current on the neutral will be less. These could be overhead or underground cables. All the new localities have underground cables. There is no new overhead construction, but most of the legacy systems still are overhead conductors. Impedance of the conductors also of the lines which we model depends on the type of the conductor, and if it is an overhead conductor, it depends on the type of the neutral wire also. Electrical Distribution System Protection Manual by Cooper, or now it is Eaton, is a very good reference for distribution philosophies that was used or adapted in the United States. So it provides tables for various conductors, for various configurations and impedance values, which could be very helpful in modeling in your distribution network. If you look at the feeder protection, I said when a fault occurs, the current changes from load current values to the fault current values, and then we can use fuses, which has a melting link, which melts and then clears the fault. Or there are reclosers, which are self-contained. These are self-contained devices which were either put in substations or outside, and along with sectionalizers, which counted the number of times the feeder reclosed and then isolated sections of the feeder, so you can restore only the partially. You can restore partially the feeder and isolating or disconnecting the faulted section. And then the modern ones, we have breakers at the substations with overcurrent devices to monitor the system and then operate under fault conditions. Fuses have a fuse link, and then it has got a cutout, and then this is the holder. This is a typical configuration, and when the fuse melts, this small tail drops off, and then if you drive around and you can see that the tail is far. If you see the tail, then you know that the fuse is blown. It was easy for the maintenance crew for a fast detection and replacement of the fuses. There are 2 main categories of the fuses: expulsion fuse and then current limiting fuse. And there are varieties of fuses available, and it depends on what that has been used. And I have taken only two examples here. The K that had a faster operating time, and the T-Link that was little slower than K, but it has more overload capabilities. These are the ones I'm using it. There is another category called type E fuse. What it states is type E fuse always clears the fault if the fault current is at least twice the rated current. Suppose if it is 100 amps fuse, if you have 200 amperes, the fuse will definitely melt and then clears the fault. And the cutouts which we use for this are also rated for specified short circuit current rating. They are typically around 10,000 amperes. And expulsion fuses, if you look at it, these emit gases when they operate. So these were always used in open spaces, whereas current limiting fuses that doesn't emit any gases are used, or ionized particles are used in confined places, or if fault current is extremely high, then that limits the current also. So if you look at the coordination of the expulsion fuses, same type of fuse links were used if one utility or distribution owner uses a T-type, the he uses T-types everywhere, or a K-type or a QA type. There are varieties of fuses available. They try to use the same type of fuse depending upon their requirement. And then current limiting fuses, I already covered this, indoor only, or in confined places you cannot use expulsion fuse as it does not emit ionized particles. There is another set of interrupting device called automatic reclosers. These are self-contained hydraulic devices historically. Now they are replaced with electronic controls with a DC battery and as a self-contained unit. And it has oil or vacuum interrupters. And then these can be mounted either in the substation or on pole tops. There's another category which we normally don't come across. These are called sectionalizers. These were used on branches of the main feeder circuit, and then what they do is they don't have the interrupting capability, but it counts how many times the current exceeded the setting, and if it exceeds a preset number, then it just opens permanently and then resets it. At the substation, we use breakers, which has got 3 CTs on the phases, and that is fed to a relay, which could be electromechanical, which was used in the legacy systems, and now it is all microprocessors, and then we use it for phase overcurrent and ground overcurrent element settings. In fuse coordination, you can just use fuses all the way. If you have a fuse at the source end, which is the highest fuse, and suppose if we say it is 200, the next fuse, which if we use 140 or 100 or 65, adjacent fuse, then it automatically had coordination. It allowed the first fuse to blow before the second one even melted. There was a time coordination curve between these two. And they had two series. One is called preferred series, 6 amps, 10 amps, up to 200 amps. Another one was 8, 12, and up to 80 amperes. And these two types of ratings were used. So the distribution folks doesn't have to look at the coordination. Fuses have inverse time characteristics. Higher the current, the faster it clears the fault. And so they don't have to look at it. If they have 200 upstream fuse, then they can go back and put 140T as the highest fuse on the low side. Or if they have 80 amps and the upstream fuse, the highest fuse that they can use downstream was 50 amperes. So they didn't have to go through coordination. It was already preset. So this was for fast restoration of the system. This is just an explanation of that. Maximum clearing time of the downstream fuse should not exceed 75% of the minimum melting time of the upstream fuse. I will show you the two characteristics in a couple of slides. And use of either preferred rating or non-preferred rating met this requirement. Relay fuse coordination, you have a relay at the substation, and then you have a main fuse feeder here, and then they have two branches here, and then these are subfused, and we have to make sure that for a fault beyond this fuse location, the fuse operates first and the relay should not operate. So we have minimum coordination time requirements, which was typically 15 to 25, as I will show you in future slides. Feeder relay settings were also based on where this feeder is actually and what type of load it was serving, where it was located, the substation, and also what type of feeder they were feeding. If you look at this, based on the system strength and length of the feeder and rating of the feeder we had, the short feeders are typically in urban areas, in cities, where you have large transformer to serve large loads. So you have very high fault currents, but the length of the feeder also was kept low because there were multiple substations in that area. Long feeders are very common in rural areas where you have a smaller transformer because the load is not that much, but it went long ways. So, and then in urban areas, you had field switching for feeder ties. So we could pick up load and serve the load from a healthy feeder if there is a faulted feeder in that area. Typical settings, first we have to make sure that the phase pickup is greater than the maximum load of that. Suppose if there is a feeder has got a load of about 300 amperes, I wanted to make sure that I don't set the phase overcurrent relay below that, but we are at least at that 300 amperes. And just to provide a margin, it was set to 135 to 150% of the maximum load on the feeder. And then it also has to operate for faults on the feeder, right? So what you do is you model the system and look at the fault currents at the end of the feeder. For a phase-to-phase fault, if it is say 1000 amperes, I normally set this phase pickup to about 50% of that. I'm taking a margin of 2 to 1. This need not be same. Depending on the comfort level and the historic usage, this ratio can vary. But in my presentation, I have used always as 2 to 1. The fault current has to be at least twice the pickup current of the overcurrent relay. So if I look at the phase pickup, the first key thing I have to look at it is the phase pickup has to be greater than the maximum load with a margin, 135 to 150. And then the phase pickup at least has to be half the minimum phase-to-phase fault current at the end of the feeder. And the ground overcurrent relay, which normally doesn't operate under healthy system, it operates only for phase-to-ground faults. It is also set so at 50% of the minimum single line to ground fault current at the end of the feeder. So with the 2 to 1 margin, I'm setting this as half the phase-to-phase current at the end of the feeder, or half the phase-to-ground at the end of the feeder. And also, it has to be greater than 135 to 150%. Suppose if the feeder fault current available is extremely high, I can just use the feeder rating criteria and set that feeder setting as 135 to 150% of the maximum load. If any of these areas is not met, then I know that I cannot protect the feeder up to that length to the end of the feeder. I have to put an intermediate interrupting device on the feeder at somewhere in between the end of the feeder and the source, so that you can cover the section from that point up to the end, and then fault currents up to that point where we put the interrupting device, you meet all this 2 to 1 criteria. Short feeders with a strong system. This is a very typical urban scenario where if I take a 13.8 kV system, you use a 15 kV cutout, fuse cutouts. They are not rated for 10,000 amps. So the fault current coming out of the substation was limited to 10,000 amperes. If we had bigger transformers or multiple transformer stations, we always went back and then put current limiting reactors so that the current coming out of the substation is not greater than the value which exceeds the fuse cutout ratings. I think fuse cutout ratings are also available for 12,000 amps. You can check with the vendors and make sure you have to limit it to the value. And also 10,000 amperes was used because most of the commercial switchgear available was all rated for 10,000 amps. that could be used by the customers. Feeder length here, I'm assuming a 336 aluminum conductor, and then the length of the feeder is 5 miles. This is just an example. And then when I take 10,000 amps and then put this the impedance of the line with the 10,000 amp source, the fault current at the end of the feeder is 1500 to 2000 amps for 3-phase fault and 900 to 1000 amps for phase to ground faults. So this is what I'm getting. So I have to set it higher than the maximum load that is set by 135 to 150, and then the settings have to be less than the fault current values on the phase and also on the ground relay. We picked up here 50% of the maximum phase conductor because it is a very strong source. So I'm just rating this on the conductor rating. I'm setting the pickup of the phase overcurrent based on the conductor rating. So it is set to 840 amperes, and the ground is set typically to 50% of that. Ideally speaking, if there is a 40 ohm or a 30 ohm impedance, if you use, these ground settings come lower. But in the urban areas, because of the short length, and also for faster restoration when we do field switching by opening one phase of one feeder and then hooking up the adjacent section to the next healthy feeder, there might be unbalanced currents. So you have to look at the field switchings, the philosophies of that is used by the distribution source, the company, and then you are setting it to about to a value which is higher than the maximum switching switching unbalance that is seen by the relay. And here it is loaded up to 75% of the feeder, so we are looking at 420 amps. And this is how a lot of legacy systems are set. Phase current is set first, and then you take 50% for the ground in the urban areas. So for a closing 3-phase fault, we get 9,200 amperes. So here is a fuse curve, and then here is the relay curve. Fuse has two curves. One is the minimum melting time at the bottom, and then this is the total clearing time. It takes some time to melt that fuse link, and then it has some few cycles for total clearing. So you get two curves, inverse curves for a fuse, whereas you get only one curve for the relay. You see that for this fault current, the fuse total clearing time was 2 cycles, and the relay operated in 23 cycles. So we gave a margin of 21 cycles. So if the fuse does not operate, then as a backup, the feeder relay operates in 23 cycles. If you look at this, then we set it up to time tap of 7 with a CT ratio of 600 to 5 and time dial of 1.6, and we used US inverse curve. These curves, inverse curves, are not standardized values. Depending on whatever that has been used in the system, you can use the same type of curve. Some people use extremely inverse, some people use inverse, then some of them use moderately inverse, and some of them use very inverse. Or you can also use IEC curves. These are the US curves, and you can also use IEC curves. So as long as you use one curve, you just use the same thing all around, so that you are using same type of coordination, and you get a good idea how to set relays if you had to go through some hand calculations. Then closing phase to ground faults also gives me 9,300 amperes, and the ground relay is set so that it operates in 46 cycles. The reason why you are set higher than this is if you reduce the time dial, the ground overcurrent relay curve gets into the fuse curve, and we don't want that. We want the fuse to always operate, and if the fuse does not operate, even the ground relay or any relay at the substation has to operate. So we have to increase the time dial to 4 here, and then reduce the pickup to 3.5, which is about 50%, which is 50% of the phase pickup. And then if you look at the feeder end phase to ground fault, I get 967 amperes. And then you get fault current to the pickup current ratio of 2.3, which is good. And you have enough coordination. The fuse took 73 cycles, whereas the relay took 374 cycles. If you look at the 3-phase fault at the end of the feeder, it is 79, and you have the ratio of 2.1, what is phase pickup versus the fault current of three-phase fault, and then your clearing time of the fuse is 20 cycles for the feeder end fault, and then phase relay took 188 cycles. This is an urban feeder which is 5 miles. I'm using 336 aluminum conductor. You can replace it with an underground cable and then go through the same coordination. And then feeder fuse coordination, again, we can look at a phase-to-phase fault at the end of this, where only the phase relays operate. The phase-to-phase fault current is about 86% of the three-phase fault. So instead of 1779, it came down to 1541 amperes. But now your fault current ratio reduced to the pickup reduced to less than 2. Preferable ratio was 2. That was our criteria. So if you want, you can go back and then reset this to 50%, which is about 770 amperes as the pickup instead of 840. You still have a margin much more. Instead of 150%, you are getting about 140% of the maximum load, which is 560 amperes. That is what we are assuming here. So now let's go to the longer feeders. If I have a longer feeders which 840 amps, typically these settings are not very high in the rural areas. But if you assume here, if the feeder length is more than 5 miles here, I may not meet that criteria of 2:1. So under such conditions, I have to put another interrupting device on the main feeder where you set another relay which is supposed to take care of the loading beyond that point, which is generally lower than the loading from the substation, because you would have a lot of other loads here that you would have served. And then you have to coordinate those relays with the substation relay. And these relays coordinate with fuses here beyond that point. This could be a recloser or it could be a device. We generally don't use a fuse here because it might you may not be able to restore for the rest of the system. You can or you cannot. You can also use fuse, but generally it is not used. So if you look at this in short, for a close-in fault, you had feeder operating time of 23 cycles, and then behind the feeder relay there is a bus where you have 2 or 3 feeders connected to that is fed by a transformer. There might be an overcurrent relay there. So if the feeder relay does not operate, you have to coordinate with 15 to 25 cycle coordination with that. So the bus relay for the same current can operate in 38 to 48 cycles, and then that is coordinated with the transformer high side. So if there are many overcurrent devices in series, you have to make sure the overcurrent device closest to the fault operates first. The next one has a 15 to 20 cycle, 25 cycle coordination with the next one. So it continues, and then your operating time increases as you reach to the high side of the transformer. And similarly, the pickup also might be higher. For example, the bus relay, which is feeding 3 or 4 feeders, you have to set it higher than the individual feeder rating. So normally this is set on the transformer ratings. And since transformers are overloaded many times, they could be set as high as 160% of the transformer rating. I'm going really fast here. That is just introducing the concepts. Please go through, look at application guides, and look at what philosophies you have adapted in the system, the distribution network, what you are using, and then you can look at it. The key point here is it has to clear for a fault on any distribution line at the end of fault at the end of the feeder. And second thing, the closest overcurrent device has to operate fast. Then instantaneous settings are also set sometimes. This is if there is a fuse very close to the substation, then and then if you have an underground section, you don't want that to get damaged for faults if you wait for a longer time. It is set to 85 to 90% of the close-in fault current, and in our case it was 97, so we set it to 8300 amperes. So this would cover instantaneous, gives instant coverage on the feeder for about half a mile. And it is not necessary that you have to use this. Depending on the reliabilities numbers which come out of the system, this is sometimes added or this is sometimes removed in a lot of distribution networks. There is another settings called fuse saving schemes. Instantaneous settings is blocked after the first reclose. Suppose if there is a fuse here very close to the substation, if there is a fault at this beyond that fuse, then in using instantaneous overcurrent relays will prevent this fuse from blowing, and then you reclose it. If it is a temporary fault, the whole system is restored. If it is not a temporary fault, then you disable the instantaneous to allow the time overcurrent to coordinate with this, and then the fuse blows, and then you get the coordination accordingly. But you get a momentary outage for the rest of the customers because of fuse saving schemes. So as I mentioned, if the reliability index changes in that region, these setting instantaneous or enabling or disabling instantaneous is very common in the distribution world. Then there are animal faults on overhead conductors because of the warmth. Sometimes there is, even though there is enable protection in a substation, you come across cases where animal gets shorted to the face and then creates a fault. These are temporary because it falls off. So sometimes one shot reclose is used on the buses. So there is an overcurrent relay. If it sees very high currents here, then you have one shot reclose to bring back the bus and restore the system. For this, you have to have an instantaneous setting on the feeder, and then you delay this instantaneous by 15 cycles to provide coordination, because if there is a close-in fault, you don't want the bus to operate and take all the feeders out. And into higher generator stations with large fault currents, you have reactors which will allow you to get this coordination without this time delay. As I mentioned here, if it exceeds 10,000 amps, current emitting reactors are used. So it is a partial differential section. So this overcurrent relay is only protecting this section. So if there is a fault here, there is one more overcurrent relay in this section that will protect bus section 2 here, if I take this as bus section 2. And then because of the fault reactor here, the instantaneous fault current here will be less than the instantaneous fault current on the bus. So it gives us a coordination to set bus instantaneous and also the feeder instantaneous settings here. Normally closed or normally open ties on multiple transformer stations also needs to be considered in settings of overcurrent, especially the instantaneous. You have to see when it is normally closed, you take the highest for current. And if there are multiple transformers, more than 2, because of so much of variations on the permutations of how many transformers are in parallel, distance relays are used under such conditions to protect the bus. And of course, if you have multiple transformers, you do have a lot of you will have current limiting reactors used on this. This is just a coordination from fuse all the way up to the high side of the overcurrent. As I said, the one which is closest to the fault has to operate first, and then the one behind this has 15, 20 to 25 cycles coordination, so that it can be taken up all the way up to the high side of the transformer. Face-to-face fault, we have taken this and given the numbers, and similarly in the previous one I gave face-to-ground faults. And long feeders with weaker resources, we have taken this, but still the criteria of 2:1 is used for the fault current. Your pickup cannot exceed half of the feeder fault current at the end of the feeder, but the pickup also has to be set higher than the maximum load. In the case of urban feeders, we did use the rating of the feeder. But in the case of long feeders and rural areas, we just look at the maximum load and set the pickup based on the maximum loading of that, which could be much lower than the feeder ratings. There is a guide called Rural Electrification Administration 61-2 guide for making sectionalizing study on rural electric systems. Here they use a fault resistance of 40 ohms or 30 ohms depending on the size of the distribution transformers used here. So your fault current reduces to 240 amps for single line to ground at a 5-mile feeder with a 30 ohm fault resistance. So your ground element are set much lower, unlike the urban areas where we took half the phase current for setting the ground. The ground elements are set much more sensitive in these rural areas. There is we don't use these numbers of 40 ohms or 30 ohms in urban areas where you have a stronger system. What has been observed in industry is either there is the current is high enough when there is a short circuit, or if it is a down conductor, the impedance is so high, the current is extremely low. But this is a rural electrification guidance, so that has to be followed. So we use 30 or 40 ohms in the rural areas. Other modern features which we use in modern relays is negative sequence functionality is available in microprocessor based relays. We do use this. And then torque control is also used for protection elements, where if it exceeds or if the voltage comes down, then only you allow the relay to operate. These are used. Because of the flexibility in the functionality of the relays, some of these have changed, but still your basic criteria is it has to clear a fault on any fault on the feeder or at the end of the feeder. If you assume some resistance for ground faults, it has to clear that. Your settings are based on that. And then the phase relays are set to serve the load, so they are set above the maximum expected load or the feeder ratings, depending on where these are used. Also, because a lot of faults are temporary in nature, we have auto-reclosing. In the case of reclosers, electromechanical legacy relay devices, they had fixed 2 or 4 second recloses on that with up to 4 trips. But in the modern microprocessor substation relays, these are settable, and high-speed reclosing and distribution is considered to be any reclose within 5 seconds. So they try to use it as high-speed reclose, unlike transmission systems where high-speed reclose is extremely fast in about 0.3 seconds in 345 kV systems. The reset time also is set longer after it recloses. You count it as one shot, and then you reset it after a very long time, because feeder end faults can have a very long operating time. That is why these are set much higher. When upstream devices or electromechanical devices or microprocessor relays are used, need to account for the reset time, because electromechanical relays have a disk which moves and it takes some time to reset, come back to the original position. So if there is a reclose, it may be halfway through, and the second time it operates, it might operate faster. So if there is an upstream electromechanical device with a microprocessor based device later on, you set so that the microprocessor based relay also emulates the electromechanical functionality.